This is a Sine by any other language. It is a journey through implementing sine wave playback in 50 different programming languages. So it's going to go through a bit quickly. Bear with me. So as Shakespeare put it, what's in a programming language? That which we call a sine wave by any other programming language would sound as sweet. So that's kind of the concept of this talk. Basically, take the sine wave playback as like a hello world of audio programming, implement it in a bunch of different languages, see if there's anything we can learn along the way. Thank you, Prashant. You already kind of introduced me. My name is David Su, audio programmer, game developer, musician, other things. These are some projects I worked on. There's my website. So sine waves, quick refresher. Sine waves are a function of the amplitude, the frequency, time, and the phase. And for these examples, I'm going to be just using an amplitude of 1, frequency of 440 hertz, no phase, keep things simple. In some cases, I'm going to be specifying like a total duration, so I'll just use 1 second for that. And here is an example of what that sounds like. It might be a little loud. I hope it's not too loud. Oh, that wasn't too loud. All right. Sine wave we all know and love. Cool. Some of these examples will also involve manually writing to a wave file. So this is the file format header that I'm using. That is the wave header format. So to choose the languages, I took the top 20 most popular languages from last year's Stack Overflow annual survey, and then also this great list of audio programming languages from Wikipedia. I've generally tried to use built-in types and functions and standard libraries. This wasn't always possible, or I couldn't always figure out how to do it. And disclaimer, I am not an expert on most, if any, of these languages, so I worked a lot off of references and tutorials, and there's probably a better way to implement every single one of these. Okay, with all that in mind, let's go. We're going to start with the general purpose languages, again from this survey. First up, we have JavaScript. This is actually a great first one because it's super simple using the Web Audio API. So we create an audio context, create an oscillator, set it to a sine type at frequency 440, connect the oscillator to the context, and then play it. This plays infinitely, so it lasts forever as long as the program is running. So technically, the last example did use HTML, but I wanted to use a different approach and one without JavaScript. So here I'm just embedding an audio file, which is not super interesting, but it at least shows like HTML audio playback support, which is cool. And this is a 1 second wave file. For Python, there's a Win Sound module, which comes built in if you're using Windows, and it has a beep function, which you can use, just pass in 440 and then 1,000 milliseconds. Again, this is Windows only. Sorry. For SQL, I had to create the sine wave from scratch. So this involved generating samples based on the formula from before, and then writing to a wave file. You can see the wave file header writing on the right. Yeah, that was probably the most painful one. But there's a tutorial that I worked off of, which was very helpful. TypeScript, this is very similar to the JavaScript example. Uses some TypeScript-specific syntax on the top there, and then it gets compiled to the JavaScript at the bottom. For Bash, or more generally Shell, I'm just using FFmpeg, which is an external library, but it's pretty cross-platform. Uses libavfilter to generate the sine, and then writes to a wave file. For Java, I'm generating the samples manually and then making use of the Java Sound API's source data line for playback. That one plays infinitely as well. In C#, we use, again in Windows, console.beep, same thing as the Python one, Windows only. C++, again, a Windows-only example. Here I'm using Wasapi, and then aside from that, just the STL. Most of the code here has to do with setting up the audio client and feeding it samples, and then this also runs infinitely. For the C example, I wanted to get out of Windows land, so I did this one in Linux, using ALSA for playback. Besides that, just using the C standard library, and I guess you can't really see it in this, but generating the samples manually and then passing it over. For PHP, we're back to writing a wave file. So manual sample generation here on the left, or actually on the right. And then also manual wave header writing. Cool thing about PHP is you can generate HTML. So at the bottom right there, I'm creating an HTML audio player, which is then set up to write the wave file that we've just written. All right. PowerShell, this is exactly the same as the Bash shell example, just using FFmpeg. The Go example, this writes both, a raw PCM file and a WAV file. So we generate the samples manually. At this point, I was getting a little tired of writing the WAV headers, so I'm using the Go Audio WAV external library for WAV file writing, but the raw PCM writing is done just with built-in libraries. Rust, this is one of those languages that I've always been meaning to try, so this is a good excuse to do that. Same in flow as the previous example, generate samples manually, and then I'm using the Hound library for writing the WAV files. The Kotlin example is implemented as an Android app, so we generate the samples manually and then use the Android media audio track for playback. For Lua, I went in a bit of a different direction. So I implemented this as a Lua rescript in the DAW Reaper. Basically what it does is it creates a track, attaches a resynth FX instance, which defaults to a sine wave, and then creates a MIDI item with the note A440 or 69, and then simulates a play call. So this is all in the box Reaper. The Dart example is implemented as a Flutter web app, so it uses the Web Audio API, so it's the same steps as the JavaScript example. This assembly code is, I didn't write this manually, it's just created from generating an assembler listing file, compiling the C++ example. So this is just using MSVC. Sorry, maybe someday. For Ruby, again, generate samples manually and then using an external library, Ruby Audio, for writing the output WAV file. And the Swift example, this is an iOS app, so we're generating the samples manually and then using the AV Foundation audio classes for playback, and then this runs infinitely as well. So yeah, we can start to see kind of some broad patterns and axes of comparison. Things like for sine synthesis, do we have to generate the samples manually, or is there like an oscillator object? For audio playback, do we get real-time audio output, or do we have to write to a file, or some combination of both? There's also stuff like fixed duration versus infinite, and also wave writing. Okay, so let's get into the more audio domain-specific programming languages, again from this Wikipedia list. So ABC notation is a language created for music notation. It works in the symbolic domain, which means we can't actually determine the absolute timbre like a concrete sine waveform. So in this case, I'm defining it's an A2 down at the bottom, which corresponds to 440. It's a half note at 120 BPM, which is 1 second. This outputs MIDI, so you could then play it back in like a DAW or something. Bool processor is a language designed for music composition and improvisation. Uses a lot of like generative grammars. Here it's also outputting MIDI. There is a C sound integration. I tried to get it working and couldn't, so I moved on. Chuck is a strongly timed language built for real-time audio synthesis and music composition. This looks pretty similar to the web audio example, where we're creating an oscillator, setting the parameters, and then connecting it to the output. RTCMix is another real-time audio synthesis and processing language. It's based on CMix, which is based on the music N family. And the general music N paradigm is you have an instrument and a score. And the instrument kind of defines the sound or timbre, and then the score defines the notes, so like pitch and rhythm. So here we're loading a wavetable instrument and then playing it via the score, and relying on the default wavetable behavior of just using a sine wave. Shout out to Brad Garton, who was the original creator of RTCMix, whose computer music seminar really got me into audio programming. All right, C major is a language built specifically for writing fast DSP code, originally created by Julian Storis, Cesaris Ferrari. Again, we've got a built-in sine oscillator, so we use that, connect it to the output. Cool thing with this is when you like create a project, the auto-generated file actually does most of the work here, so I didn't really have to do that much. Common Lisp music is a music synthesis and DSP language, also derived from music N. So here you can see we have an instrument on the right, and then the score on the left for playback. And we are manually calculating, or no, we're not, sorry, we're using the make oscill function there. Okay. C sound is an audio programming language also based on music N. Here we define a synthesizer that contains both the score and the instrument, and we use this p oscill A function for the sine instrument. Extempore is a live coding language and environment, and here we're defining a Sine generator and then just using it as our main DSP function. Faust stands for functional audio stream. It's built for audio synthesis and processing. The os.osc function does all the work here, and Faust famously it compiles to all sorts of targets like this really cool web IDE here. Glycol stands for graph-oriented live coding language, and this might be the shortest example in terms of character count, very streamlined. Basically, we're just setting our sine oscillator to the output. The hierarchical music specification language, or HMSL, is designed for music composition and performance, built on top of Forth. This example uses their score entry system. Down there, it's the play now 11A4. It does output MIDI instead of audio. Impromptu is the precursor to extempore. Both were developed by Andrew Sorensen. You can tell the implementation here looks pretty similar to extempore. Sadly, I couldn't test this because the app is 32-bit, so it doesn't run on my Mac, but maybe down the line. Ishilang, I think that's how you pronounce it, is a live coding environment. It's built on top of SuperCollider, and here you see the sign parentheses 6, the 6 being A, which is the 6th scale degree for the default C major. JFugue is a Java library for programming music, so it outputs MIDI since it's symbolic. Cool thing about this is that you can actually work in microtones, which I think is pretty unique for a MIDI-based library. JMusic is another Java music programming library. This one does have a library of instruments you can import, including a simple sine instrument. So that's what I'm using here. You can definitely see the music and inspiration here, where you've got the score and the instrument. JSyn is a Java library for synthesis and DSP, created by Phil Burke, who also created HMSL. Here we've got, again, this oscillator to output paradigm. KeyKit is a MIDI programming environment, so again, outputting MIDI, so we don't get sine playback. But I like this. I really like this interface here. Comes from the 90s, if you couldn't tell. Kima is a hardware and software sound design environment. This is another one that I wasn't able to run myself because it requires the Pacamara audio processing unit, which I don't have. So I grabbed a screenshot from this YouTube video. If anyone has one of these, please let me know. They're pretty expensive, and sorry. Lily Pond is a music engraving format. Like ABC, it's notation focused, so we don't get any actual playback here, but again, it's outputting MIDI. MaxMSP is the visual programming language we all know and love for multimedia and computer music. Super simple oscillator to output. Mercury is a live coding language designed around accessibility, and here we're setting up a sine synth, the scale, the tempo, and then playing the note. Music macro language originated in the late 70s for sequencing music in like early video games and chiptune. This example is created using a newer IDE as well as syntax flavor. Music N is kind of the grandfather of all of this. It's a family of programming languages coming from Max Matthews' original music, or Music 1, from 1957 at Bell Labs. The example here is Music 5 from 1966, but it's running in M5 Live, which is a more modern environment that uses the same syntax. And so you can see the instrument definition in this first block, which defines our sine oscillator, and then the score portion at the bottom, which actually plays the note. Nyquist is a synthesis and composition language. It's quite flexible. You can see a lot of different ways to achieve the same sine playback, all very simple, some of the commented ones there. And it has its own cool IDE. Open Music is another visual programming environment created by the folks at IRCAM. Here we're using OM to C sound, so I'm basically just wrapping around the C sound example for the actual sine synthesis. Orca is an ESO-Lang and live coding environment. It doesn't do synthesis, so here we're sending MIDI to Ableton Live. I guess this might actually be the shortest one, but you can see the play MIDI note, blah, blah, blah stuff to kind of see what's actually going on. Pure Data is another visual programming language for computer music created by Miller Puckett, who's also the original creator of Max. So Pure Data, or PD, is often kind of positioned as like an open source alternative to Max MSP. Very similar implementation here, oscillator to output. Tidal Cycles is a live coding environment embedded in Haskell and also uses SuperCollider to produce sound in the backend. Here we're defining the note, the octave, and the sound, and then evaluating that to produce the sine. Reactor is a digital modular synth created by Native Instruments. Again, we've got our parameters to our sine oscillator to our output. Sonic Pi is a live coding language and environment. It's designed with education in mind, which is really cool. It's super beginner friendly and easy to install. Also uses SuperCollider under the hood. And here we're using the sine synth and then playing back the note. The structured audio orchestra language is part of the MPEG-4 standard. You can see this instrument score paradigm here too. I also wasn't able to test this one. I couldn't get the compiler running for similar 32-bit issues. SuperCollider, we've already seen this as the backend for a few of the other languages. It's a platform for audio synthesis and algorithmic composition, originally developed by James McCartney in 1996. And yeah, we're just creating an oscillator and playing it. SynthEdit is a modular audio environment tailored for plugins. Looks like the Reactor example, and yeah, parameters, oscillator, output. I like this like 5-volt analog analogy. It's pretty cool. So just as a bonus, as a game developer, I wanted to include some game audio stuff. This is Unreal Engine, specifically Metasounds, which shipped with Unreal Engine 5. Allows you to do a lot of cool procedural audio things. Again, parameters for this sine oscillator connecting it to an output. And then Wise, which is one of the most popular game audio middleware solutions, has a built-in sine generator as well. All right, so yeah, a lot of axes we can compare these by. Generally, there's a lot more built-in synthesis capability. One notable difference, we have like audio versus MIDI. We see a lot of visual languages, and really cool seeing like the lineage and history, just looking at Music N and SuperCollider and how they've like spawned all sorts of other languages of their own. Okay, so quick video recap. This is all the languages I could actually run, which is 52. All the video and audio is actual capture, and I had to hard code the frequencies for each because it was quite last minute. All right, thank you. Source code and references there. Yeah, thank you so much.